Yeah. Yeah. Okay, so today I want to prove the main theorem for this course, and that is the localization formula for a circle action. Okay? So this formula says that if you have a circle action, then for a circle action, the integral of an equivariantly closed form can be written as a sum over the fixed point set. Where each fixed point contributes some multiplicity. Okay? So so it's a way of converting integration to a finite sum. Okay? And when we work it out, we'll find what that multiplicity is. Okay? Okay, now, in order to prove this formula, well, first we have to know how to integrate an equivariantly closed form. And we will also need Stokes Theorem. So we need manifolds with boundary. Okay, so let's first look at manifolds with boundary. Okay. Now, if you have a manifold with boundary, then locally, an interior point just looks like an open subset of Rn. So that's no different from a manifold. But a boundary point, okay, locally looks like the upper half space. Okay, so if M is a manifold with boundary and P is a point in the boundary, then locally at P, so there exists a neighborhood U such that, okay, so U, this is U, is homeomorphic to an open subset of an upper half space. Okay, so Hn, that's the set of points in Rn where, say, Xn is greater than or equal to 0. Okay. And then we can define the tangent space at P. Okay. If it's an interior point, it's no different from a manifold. But if it's a boundary point, well, you still define it to be, now, tangent vectors are derivations on germs of C infinity functions. So it's the same definition, derivations on germs of C infinity functions at P. Well, you see, if it's, okay, now in the definition, you only require homeomorphism, but then this becomes a chart, and so this homeomorphism will be a diffeomorphism relative to the chart. And the boundary will be smooth. Because it locally, I mean, maybe instead of defining it, I'll just state a fact. So once you have, I mean, I'm assuming that you have seen manifolds with boundary before. Okay? So once you have put a differentiable structure on it, so the boundary will be smooth. Okay? I'm only defining manifolds with smooth boundaries. Yeah. It's also possible to define manifolds with corners, but I'm not defining them. Okay, so we're only working with manifolds with smooth boundaries. Okay, so now if you have local coordinates, okay, on the upper half space, you can still differentiate with respect to all the variables. Right? So the tangent space is still the vector space with bases ddx1, ddxn. Okay? I mean, you still have these vectors. Okay? Now, this is also in the tangent vector. But there's no curve with that as the initial vector. Okay? So that's the only difference. But this is still the tangent space. And then the cotangent space is a dual. So it's the vector space generated by dx1 to dxn. Okay? So we can still talk about, so now you can have the tangent bundle over a manifold with boundary and the cotangent bundle, and we can still talk about smooth differential forms on a manifold with boundary. So locally, it will be. It just looks like this. See, the only difference is that. Let me see. Yeah. No, there's no difference between having a manifold and a manifold with boundary. Tangent vectors look like that locally, and differential forms, they look like the wedges of these locally. So everything that we have done so far for manifolds, we can do for manifolds with boundary. You can talk about action of a group on a manifold with boundary. We can talk about equivariant forms on a manifold with boundary. Okay, so now I want to define the integral of an equivariant form for a circle action. So if, say, omega is an equivariant form of degree k, then it's a polynomial in U with coefficients that are invariant forms. So omega will be equal to, the constant term will be polynomial degree k, and then you have a linear term U, so then the coefficient will have degree k minus 2. Okay, and then k omega k minus 4 u squared. Okay, so it will look like this. And we define the integral of omega to be just the integral of the coefficients. Okay, so that's the definition of the integral of an equivariant form. Now, normally when you integrate, you get 0 unless the form has the same degree as the dimension of the manifold, right? Yeah. So normally you can only integrate a form of degree n on a manifold of dimension n. But when you have an equivariant form, you can integrate an equivariant form of any degree on a manifold dimension n, because one of these might be just right? So even if k is too big, maybe k minus 2 is equal to n. then this will be defined, and the other terms will be 0. Okay? So now, first of all, let's see. What happens if k and n have different parity? If k and n, which is the dimension of n, have different parity. That means one is even and the other is odd. Then the integration is always 0 because k and n, they have different parity, so they cannot be equal, right? So this will be 0, but k minus 2 and n still have different parity, you see. All the coefficients, all the degrees have the same parity. So if k and n have different parity, then the integral of omega k over m is 0. The integral omega k minus 2 over m is 0, etc. So the integral of omega over m is 0. Okay? If they have different parity, then the integral is automatically 0. Now, what if they have the same parity? Say k is equal to n plus 2m. Okay? M can be positive or negative. Now, okay, so if k is greater than n, this will be 0, but after you subtracted enough multiples, one of these will become n. So the integral, see, all of these integrals will be 0 except for the one that's of degree exactly n. So it will be the integral of omega n over m. That will give you a non-zero number. And then the total degree is k, so u has to be raised to the power m. Okay? So if they have the same parity, the integral is just this. This is if for k greater than or equal to n. Now for k less than n, well, all of these terms will have degree less than n, so you'll get 0. Okay? So, okay. So that's the integral of an equivariant form. All right, and now we need Stokes Theorem for equivariant forms. So Stokes Theorem says, okay, suppose S1 acts on a compact oriented manifold M with boundary yeah, now I have to assume that now I think there's a theorem, right, that says if you have a smooth map of a manifold with boundary, then boundary points will go to boundary points. Okay? Mm-hmm. That's in my book on manifolds. So automatically, S1 will act on the boundary. Okay? I mean, I'm always assuming that this is a smooth action. Okay, and then we have an equivariantly, just an equivariant form. So if omega is an equivariant form, then Stokes theorem says the integral of dx omega is equal to the integral omega on the boundary. Okay? Now let's say we need to, it's better if we just look at omega of a single degree. So if omega is an equivariant form of degree k, then you have this statement. Now k, unlike the usual Stokes theorem, where k has to be of degree n minus 1, right? It has to have degree 1 less than the dimension of the manifold. Here, k and n are completely independent. Okay? So, k is independent of n, the dimension of n. Okay? These are just two arbitrary positive integers. Mm-hmm. Mm-hmm. Okay. It's actually very easy to prove. So prove. Okay. So first, suppose k plus 1, that's the degree of this, dx omega, and n have different parity. Okay. Then why is Stokes theorem true? Well, this has degree k plus 1. This has dimension n. They have different parity. If they have different parity, then the integral is 0, right? So in this case, then this integral is 0. Okay? But then this has degree k, and the boundary has degree n minus 1. So these also have different parity. So the integral omega over the boundary is 0 for first degree reasons. Okay. And so now assume that k plus 1 and n have the same parity. So k plus 1 is congruent to is equal to n plus 2n. Okay, then bx omega m is equal to. Okay, so what is dx omega m is going to be equal to? I'm going to write. I mean, omega has degree k, so it's going to look like this, right? Yeah. Yeah. So that's going to be our notation. Omega is that. Okay. And yeah. So what is this integral going to be equal to? I mean, which term are you going to get? Is this right? Yeah. So you're going to get only d omega, what? n minus 1, right? Because then this will have degree n. So you can integrate over a manifold dimension n. And then, so n minus 1.
But there should be a contraction of.
There should be a u something, right?
I think there's the ix of
Yeah. That's right. Yeah, you're right. So let's see. Let's first do this. This is the integral of d omega minus u ix omega. Right? That's the definition of dx. And then this term here will give me d omega n minus 1. And then there's a u, right? Let's see. So u is going to be raised to the power n. Right. Yeah, because m minus 1 plus 2m is k, right? Right. So that's the first part. And then you have minus u, the integral of ix omega. Okay? Okay, now here, all the integrals will be 0 except for 1, right? So, which term will give you a non-zero contribution? Yeah, I mean, ix omega has to have degree n, so this has to be n plus 1. Okay. All the other terms will have the wrong degree, will give you 0. m plus 1, and then there's some power of u. But the only problem is that m is a manifold dimension n. Okay? So a form of degree n minus 1 is automatically 0 because this degree is bigger than the dimension of n. So this is automatically 0. So you don't have to worry about that term. Okay? Yeah. And so we have only this. But then this is an ordinary form. This is the ordinary exterior derivative. So by the ordinary Stokes theorem, this is the integral of omega n minus 1 over the boundary of m. This is my ordinary Stokes. But this is just okay. Now let me put it here. Yeah. But what is this? It's just the integral of omega over the boundary, right? You pick out the term of correct dimension. So that's equal to the integral of omega over the boundary. Okay. So that's Stokes theorem for equivariant form. So you see that it looks the same as the ordinary Stokes theorem. Yeah. Okay. And now I want to explain, why there should be a localization theorem. Okay. So now this is a very, very useful technique. And in fact, Raoul Bott used the same technique many times to prove many different theorems. He proved this localization theorem. He had proven earlier a residue formula for characteristic numbers, in terms of the fixed points of a vector field. And all of his proofs, they are all based on the same idea. Okay, so it goes like this. So suppose S1 acts on a manifold M with only isolated fixed points. Okay. In that case, the dimension of M has to be even. Why is that? If the fixed point is isolated, then we prove a theorem, right? We prove a theorem about the tangent space at the fixed point. What did we prove? Yeah, so the tangent space at the fixed point, is a representation of the circle. And we prove that if the point is isolated, then it does not have a trivial representation. A trivial representation is dimension 1. And all the other representations, all the other irreducible representations are two-dimensional. So the tangent space is the direct sum of irreducible two-dimensional representations. So it has to have even dimension. Okay? Yeah, then the tangent space has no trivial one-dimensional irreducible representation, and so it's a direct sum of the two-dimensional representations, okay? Where L is the standard two-dimensional representation of the circle. Mm-hmm. And so the dimension is even. Now, because S1 is compact, so you can put an invariant metric on M. We can put an S1 invariant Riemannian metric on M. Okay? Then S1 acts by isometry. And so around each fixed point, you put down an open ball of radius p epsilon. Okay, so this is M. Around each fixed point, let Bp epsilon be an open ball of radius epsilon. Okay? And because S1 acts by isometries, it is going to map each open ball to itself. And so it will map the complement to itself. Okay? So S1 acts on M minus, let's take out all the open balls. Okay, where P is in the fixed points set. So let's F. The fixed points. Yeah. Okay. Okay. Now, then what can you say about this action of S1 on the complement of the open balls? There are no fixed points, right? So S1 acts on this without fixed points. Okay. And if the action is without fixed points, then this is an S1 action. So the stabilizers are closed subgroups, but they can't be S1, so they're discrete. Therefore, the action is locally free. Okay? Now, for a locally free action, we found an alpha. So we fix an element of the Lie algebra of S1. So usually we fix it to be 2 pi I. This is in the Lie algebra of S1. And then you have a fundamental vector field. And for locally free action, we found an S1 invariant one form theta, which I used to call it phi, but I'll call it theta. So theta is S1 invariant, such that theta applied to x bar is 1. Right? We found that form. And then we constructed an equivariant form whose dx is 1. And an alpha, which was in the localized Cartan model, such that dx alpha is 1, right? And do you remember the formula for alpha? Alpha is equal to, okay. Now you might not remember, but it's actually kind of important to know what it is exactly, okay? So alpha was minus theta over u, and then we inverted 1 minus d theta over u, d theta over u plus, let's see, so I think, yeah, the manifold has dimension 2n, so the manifold has dimension 2n. So you can only go up to d theta to the n minus 1, right? Yeah, because if you have d theta to the n, then the degree here would be 2n, and theta has degree 1, then you'll end up with 2n plus 1. Okay, so that's the formula for alpha. And with this alpha, we can define a cochain homotopy. K from the localized Cartan complex to itself the cochain homotopy should have degree the cochain homotopy should have degree minus 1. Oh, yeah. What is the degree of alpha? Now, theta has degree 1. So d theta has degree 2. U has degree 2. Okay, so this has degree 0. All of these have degree 0. So what is the degree of alpha? Minus 1, because theta has degree 1, U has degree 2. Okay? And so, yeah, K has to have degree minus 1. And then?
That's not form on n, because you have to subtract all the balls. Alpha is theta will be.
I see. Yeah, well, okay. Now, let's see. Let's forget about that for a minute. This is just, for a locally free action, let's say on M. Yeah. Okay. So this is, I'm just reviewing what we did before. Okay. And then we're going to replace M by this. Okay. Yeah. So for a locally free action on M, we found this. This is all review. So K, you can define K omega by just multiplying by omega, alpha. Then it has degree minus 1. And, okay, we didn't check this, okay, because we proved that the localized cohomology was 0 just by saying that a closed form will go to an exact form, right? So, but this K is actually a co-chain homotopy. K dx plus vxk is the identity, okay? So, yeah, this also tells you that the cohomology, the localized cohomology is 0. But, I mean, this is very easy to check. And so, okay. Okay, so that's the review. And now, replace M by M minus all these open balls. If phi is equivariantly closed on M, then phi is equal to K dx plus dxk applied to phi. Okay, this is only on M minus the open balls. Okay, because on M minus these open balls, the action is locally free, and so you have this K. Okay, and if phi is equivalently closed, this term goes out, then it's dxk phi. Yeah. Okay. It's on this. Yeah. And then so then now let's integrate phi. So the integral of phi over M minus the open balls is equal to the integral of dx k phi. Okay? And now this is the whole trick, that you write a form as an exact form, okay, over the complement of some open balls. Then you can apply Stokes Theorem. So by Stokes Theorem, this is the integral of k phi over the boundary of this. Now M is a manifold without boundary. Maybe I should have stated it explicitly in the theorem. M is a manifold without boundary. Okay? But we took away these open balls. So what is the boundary of this? Yeah, it's going to be the disjoint union of the boundaries of the open balls. So it will be the disjoint union of spheres centered at P. Okay? So the boundary is going to be, so this integral is actually going to be the integral over these spheres with center P and radius epsilon. And what's the dimension of the sphere? 2n minus 1. The dimension of m is 2n minus 1. So it will be, the boundary will be the spheres with center P and radius epsilon, have dimension 2n minus 1, okay? And you integrate k phi. That's right, you integrate k phi over these spheres, and you have quite a few of them, so you sum them up. But you have finitely many of them because your fixed points are isolated in a compact manifold. So you have finitely many. So P is in the fixed point set. Yeah, you see. So we have turned. Okay.
How about the sum?
Pardon?
Should the manifold plus the rotation?
Sorry.
What's the rotation on the sphere?
Oh, you're absolutely right. Yeah, because this is the boundary with the boundary orientation. Now, the boundary orientation is oriented by outward normal. Okay, so but now when I integrate over the sphere, the usual orientation of the sphere is the sphere with the outward normal. The outward normal for the sphere. So the orientation is just the opposite. So I need a minus sign here. Yeah. And then this is the usual orientation of the sphere. Okay, that's right. Very good. And so you see, now, as epsilon goes to, so so you just need to compute this, okay? And you let epsilon go to 0. You make the ball smaller and smaller. So then this is just going to be the sum of some number, Cp. Okay? So if you can compute this, then you have a localization formula. You have turned an integral into a finite sum. Okay? So in the next hour, we will try to compute this. Then we have a localization formula. Okay, so let's take a break for 10 minutes. But I have two announcements to make. The first is that, so next week we'll have 2 days of classes, and then after that on May 1st, we have just 1 hour on Monday, May 1st. Okay. And that will be the end of the course. I have the last problem set due next Friday, so I'll grade it and I return it on Monday. And so everything will be over on Monday. And so I thought I would have a party. I will have a party at my grandfather's old house, where he used to live. 杜聪民国故居. So he used to live near 林森北路 and 长安东路. So we'll have a party there. We'll first go to dinner, and then we'll go to his house. It's empty, we can have a party there. Yeah. So that's next Monday. Not next Monday, the Monday after, May 1st. Yeah. Okay, so you can, I will send you an email message and you can reply because I might have to make a reservation at a restaurant nearby. Okay. The other thing is that, now I have to give several talks, at other universities to undergraduates or graduate students. And they want it to be in Chinese. So I have a talk kind of prepared, but it's in English. So I wonder if one of you can help me, translate it into Chinese, because the problem is I don't know the Chinese terms for some of the words, like sphere or open set or ball or cohomology,
You mean a talk for undergraduates?
Not undergraduate, for graduate students.
In the department?
No, not in the department. I am going to 成功大学 and 师范大学, Yeah. I think probably Taida, the students in Taida probably all know English pretty well. But
actually, in our classes, we usually we always leave the terms in English. And describe in Chinese.
Okay.
Say homology is better than 同调.
So what's homology in Chinese?
同调.
Homology is 同调. Huh? 同调要怎么写？
一个眼，在一个周。左边是眼。
同调，同调. This is homology. And what's cohomology? 上同调. Yeah. Yeah, I see. Yeah. Yeah. Well, I'm not going to talk about equivariant cohomology. I will be talking about the Lefschetz fixed point theorem. Yeah. So what's a fixed point theorem? How do you say fixed point theorem?
不动点定理.
啊？
不动点定理.
不动点定理.